Hello and welcome to the CSCI 326 Database Systems Midterm Review for Fall 2024 at AURAC. We'll start with Lecture 1, Information Models and Systems. So we start with the definition of a resource, which is any asset that is of value to an organization, which means, well, it's vague here, and that's intentional. It can be anything like generating profit, some kind of benefit, happiness, whatever, okay? And that incurs costs. And costs, again, can be of different types, can be money, can be time, can be mental strain, effort, whatever it is, okay? Or even other resources. Okay, now, point of this is to say that data and databases are resources. And the reason is because they have value. This data is useful. You can sell it. You can process it to like get some kind of benefit and so on. And it incurs a cost because in order to store the data, you need to have, storage devices, a big computer that, has the software to manage the database. And you also need someone to do the managing, which is the database administrator, okay? And you need to pay their salary. They need to spend their own time, and that itself is also a cost, okay? Hence why this is also a bullet point, or sorry, a point here. Next, we distinguish between data and information. Data is just raw facts, usually numbers, sometimes strings, and so on. And it's just stored like that in the database, okay? When you look at it, you can see like some things about a specific record. You can understand maybe like a few records, 100 records at most, if you really spend time on it, but you're not really going to be able to observe any serious trends by yourself unless you spend too much time on it, okay? So that's why you get information. You use certain tools to generate information based on that data, which means they process the data and, let's say, creates a report, like certain charts, graphs, whatever, based on the trends and trends, averages, whatever in the data, okay? Now, what is the data model? It's a collection of conceptual tools for describing data, relationships, and so on. It's very powerful in expressing and communicating the business requirements, visually represents the nature of the data, the business rules governing the data, and how it will be organized in the database. Okay? And the data model allows you to describe the database at different levels. One of them is the physical level, which is like the lowest one, how the data is actually stored in the database in the computer. The logical one, which is a little higher, at a higher level of abstraction, kind of. And the view level. There's also the conceptual level, which we'll cover in a bit. So, yeah, conceptual level. So, at first, when you want to make a database, you have to look at the real world, okay? What are the things you want to model to begin with? What is the data that you want to store, okay? And then you have the conceptual model, which after you get all this information from your own thinking and reasoning, you're gonna determine what are the kind of common points there. Like, for example, the entities. Suppose you're managing some kind of business and you're selling to customers. Each of your customers is an entity, okay? And then you notice that there are certain common points in those entities. Like, for example, each one, let's say, has a name, an age, gender, a job, maybe, if you really need to store that information, whatever, okay? And these common points, when you notice there are many entities that have like similar kind of attributes, okay, then you have an entity set, okay? So every element of the entity set has the same kinds of attributes, and attributes, like we said, name, age, whatever, it can be anything, any kind of number or string, anything you like. And then you also have the relationships between the entity sets, okay? We're gonna cover this in more detail when we go over the entity relationship model, that one, okay? At the next level, we have the logical model, which has metadata, data about the data. That means like what are the data types, how much space they take up in memory, in storage, sorry, things like that. And data aggregates, we're gonna go over that in more detail later, so don't worry about it. And we have the schema, data dictionary, also gonna be covered later. And finally, we have the physical level, data occurrences. This is called the extension, and the logical model is called the intension. The extension refers to the actual occurrences of the data. That means the different records and the table and so on, if you've seen that, which you should have. The files, how is it structured, and so on, okay? And this basically covers everything that I just said. Okay, you have data definition languages and data manipulation languages. Usually these are part of a single thing called the data sublanguage. Okay. SQL is a data sublanguage. It can be used to define the database, like what is the database, what are the different tables in it, what are the different attributes for each of those tables. And then you have the data manipulation language part of the of SQL, let's say, which is used to process a database. So what kind of things to like you have the different tables, you want to get specific information out of it, you can use the DML, okay? And this is called a sublanguage because it's not as general or as powerful as a general purpose programming languages, as a general purpose programming language, such as C and C and C and C, okay? Next, characteristics of a conceptual database model. Yeah, it's at a very high level of abstraction, so it does not depend on the model used by a specific DBMS, okay? It's independent of the physical implementation related, and importantly, we'll see this in a bit, it's flexible enough to allow changes as new information needs arise, okay? Which means suppose you realize, oh, I need to store a different type of data, one more type of data. I need to structure things in a different way. When you're at the conceptual level, it's very easy. Once you get to the physical level, it's going to be hard, okay? And that's why in the stages of database design, developing the conceptual model necessarily has to be very early. And there's a lot of looping that happens. So when you're designing the database for a customer, let's say, you're going to interact with them, ask them, is this exactly what you need? And so on, okay? Once everyone's satisfied, you're going to choose the DBMS, and you're going to make the logical model, like defining the different types of data and so on. And then you have the physical model, which is implemented using the database management system. And then you evaluate the the physical model. So how does it perform? How easy is it to use, and so on. And based on that, you can like find certain choke points or like hotspots of performance, and that's when you do some tuning to improve the performance. If you don't like what you have, you can start all over again, or you can go through here, it doesn't really matter. Finally, you have the deployment or the implementation of the database system, okay? And these are the stages. The next 10 slides cover all of that. We're not going to bother. If you want to do the reading on your own, Again, more power to you, okay? Next, the data dictionary. This is roughly at the logical level. It contains metadata, okay? It tells you like what kinds of data are being stored, what properties do they have, and so on, okay? And it can be part of the database management system, okay? So in addition to being at the logical level, it's also kind of at the physical level, in the sense that it's actually there, and the database, when interacting with it, you are making use of the data dictionary, okay? A lot of text. Project management software. I guess this is fine for the project if you want to do it. Not relevant to the midterm, really. Let me take a look at that 1 second. Okay. Yeah. If you want to make like, if you want to use project management software to do the project, go ahead. Database administration. The DBA is responsible for the design, operation, and management of the database. It's primarily responsible for planning it, designing it, developing it, managing it, everything, okay? Although the higher level design can be done by the database designer rather than the administrator, okay? These are some properties of the DBA, doesn't really matter. Planning and design stage of the database. Again, we basically just covered that. Development phase. Okay, so this is kind of splitting this thing into 2 steps, okay? Where were we? Here. Okay, this is kind of at the implementation stage or a little after it. From ensuring database security, you need to make sure it's secure. The system that's accessing the database or interacting with it is not compromised or doesn't have any kind of vulnerabilities. And yeah, ensuring compliance with good security practices. And then you have to check the performance of the database. This is actually quite relevant. Like, for example, let's say your data is organized in a really weird way and it doesn't play nicely with the cache memory, let's say, of the computer. Performance is going to suffer when you do really large queries. Okay, tuning and organizing. You can reorganize stuff. You can do this even at the logical or conceptual level, but after deployment of the database, this is going to take a lot of effort to do. And that's why you need to kind of iron out all of those issues really early before you get to the implementing, okay? And that concludes this lecture. Moving on to lecture 2, database planning and database architecture. This lecture will cover data models at different levels, and more specifically the entity relationship or ER model, which is at the conceptual level. Okay. This was already covered in the previous lecture, so we're not gonna focus too much on it. However, I do want to draw your attention to the intention or the scheme of the database, which is basically just another term for data model, but this is contrasted with the extension of the database. Now, the intention basically says what is the design of the database, what is its structure, and then you have the extension, which describes the actual data that's stored there, okay? And the extension changes very often whenever you add or remove data or modify data, okay? The data model is defined as an abstract model that organizes data description, data semantics, and consistency constraints of data. It emphasizes on what data is needed, okay, and how it should be organized instead of what operations will be performed on the data. Data model is like an architect's building plan, which helps to build conceptual models and set a relationship between data items. that's all you need to know from here. We're gonna focus on the entity relationship model in this course, so don't worry about the UML. Okay, why use the data model to begin with? The primary goal of using the data model is to ensure all data objects acquired by the database are accurately represented. It helps design the database at the conceptual, physical, and logical levels. It helps to define the relational tables, the primary and foreign keys, which we are going to see later, both of these, as well as the sort procedures, which are not really important, I believe. Don't worry about them too much. Now, it provides a clear picture of the base data and can be used by database developers to create a physical database. Not really important. Also helpful to identify missing and redundant data, which we are going to cover later. And finally, we have the last point. Though the initial creation of the data model is labor and time consuming, it's just ideas. You need to like play around with them a lot, and eventually you're gonna figure out the kind of a proper way of representing the data, of modeling it. And if you spend enough effort on this and do it properly, you're gonna thank yourself later, okay? Because it's gonna make your IT infrastructure much easier to scale, upgrade, maintain, and it's also gonna perform faster, hopefully. So, types of data models. There are mainly three different types: conceptual, logical, and physical. We already covered that. The conceptual defines what the system contains. The logical describes how the system should be implemented before discussing the DBMS. And finally, you have the how of the system's implementation using a specific DBMS. So this is before you get to, no, sorry. So this is before you get to the DBMS, and this is after, but both of them are about the implementation. So this one, for instance, is gonna have like the data types of different attributes, how much storage they take, like let's say the name of a customer entity, name attribute of the customer entity is gonna take up, let's say, 5 bytes of storage. Very little, but bear with me, okay? Conceptual level data model is gonna just give you a very high level abstract idea of what kinds of things are there and how they're related. Okay, this is not really important except for here and here. Okay, so the database instance is the actual data stored in the database at a particular moment, and it's also referred to as the database state. Okay, and this changes whenever the database is updated. So whenever you add data, remove data, modify data, like I said about 5 minutes ago or something. Okay, now that's the database state. And when it comes to the schema, it doesn't change as often because in theory you should have thought about this a lot at the start of the design of the database and then like kind of fixed it. You're not gonna change it again. Okay, so that's called the intention, and the database state is called the extension, as we mentioned earlier. Moving on to the entity relationship model, you have entities, which are the real-world objects about which we're collecting the data, and each of those has certain attributes. And there are relationships between the entities. The entities of similar types are grouped into entity sets. And we also have relationship sets, which are sets of relations between the entities. The relationships themselves, or the relationship sets, sorry, can also have their own attributes. And all of this information is encoded in the entity relationship diagrams. Okay, so first we have the rectangle, which means the entity set itself. So this is an entity set that describes the student. So there are many entities within this entity set. And each student has perhaps multiple attributes, each of them represented by an oval. And then you have relations between the different entities, okay? And those are represented by diamonds. And then whenever you want to do some linking, you're going to use just plain old lines. So here's a link between a student entity and the student ID attribute. You have a link between the enroll relationship and the grade attribute of that relationship. And you can also have a link between the entity and the relationship. Okay? Amazing drawing, by the way. Okay. The simplified ER diagram. This is one example of an ER diagram. You have the student entity and the class entity. Okay. It has this one has 5 attributes, which are the last name, student ID, credits, major, and first name. Student ID is underlined, which means it's a primary key. Similarly with the class number over here. You have a relationship between these two entities, and the relationship has an attribute itself, which is great. Relation, we're gonna cover this in next lecture or the following one, so don't worry about it too much. This is not particularly important. You can read it if you want. This is all of the stuff we did. Okay, attribute domains. Now the domain defines what the possible values can be for an attribute. Okay, so let's say you have, as the example says, an attribute called credits. The domain is going to be between, let's say 0 and 150, depending on how the university computes credit hours. Like some of them have like 300, but then each course has like 6 credit hours attached to it, or whatever you want. Okay, so this is the set of all possible values. It's just a theoretical construct. When you're implementing the database, you're not gonna actually have like a domain, hey, 0 to 150. No, you can have like certain enforcements, constraints in the implementation, but they're not explicitly gonna say that the attribute has to be in this set of values. Okay, another thing is that attributes are kind of a function. Okay, theoretically speaking, anyway, they're a function from the set of entities, that is the entity set, to the domain of the attribute. Okay, so this entity gets mapped to by the function to the element here 6. This is really crowded. 1 second. Okay, so this guy maps to 6. Applying the function of this on this guy gives you 120, and so on. Okay, and it's not necessarily the case that an element here has to map to something. It doesn't have to be the case. Okay, and you also don't need it's not always the case that an element of the domain has to be mapped to by only a single element of the entity set. You can have multiple, or you can enforce that only one is mapped to it. We'll see that in the future. Attribute null value. The value of an attribute is unknown at the present time or is undefined for a particular instance. Yeah, some some attributes, it can be okay for them to be empty, which means that they have no value. Multi-valued attributes, I suppose that's this one here. You use a double oval around the attribute's name, and the email address has multiple values. Let's say the personal email address, the institutional email address. In my case, it's well, I don't need to say it, but it's at AURAC something. Okay, and then you have my personal, which is like, let's say Gmail or some other exotic service. Now, composite attributes. also known as aggregate attributes. These are attributes that are composed of multiple other attributes. They're not entities, they're just attributes, okay? And in this example, it's the address, and the address can be split into the street, city, state, and zip code in this case, okay? So if, let's say you want to ask for the street of the faculty, which street they live in, you're just gonna get this thing, okay? But if you ask for the address, you're gonna get all of those at once, okay? Derived attributes, that's gonna be the age attribute here. It's represented with this kind of what's it called? Whatever, okay? And the thing with derived attributes is that they're calculated from a different attribute. In this case, you use the date of birth to calculate the age, okay? And you're not gonna store the actual age. However, you have explicitly defined that, hey, you can get the age of the faculty. It's not stored, but you can get it by doing some calculation using the date of birth, okay? Yeah, that concludes this lecture. Moving on to lecture 3, we're gonna cover firstly relations. Notice that we're on slide 18 because it follows more directly from the previous lecture's material. So we're going to start here and then continue back with the slide 1 to 17, okay? Now the point here is about relationship types, yeah, what types of relationships there are, and the properties that these types of relationships have. The first property is going to be the degree of the relation. So we have different types of, the degree refers to how many entity sets, are participating in the relationships, okay? So a binary relation is a relation between two entity sets. The ternary relation is a relationship between three entity sets. So this is a ternary relation because there are three entities, rectangles, that are linked by this diamond, which is the relation. You can also have unary relations, also known as recursive relations, in which a single entity is related to another entity in the same entity set, okay? Let's say you have a person, a person befriending another person, okay? This is a recursive relation. Finally, we have the n-ary relations, in which some unspecified number of entity sets is participating. So n-ary for n equals 4, which means 4 entity sets are participating. Ternary is when n equals 3, binary is when n equals 2. You can also have n equals generally any positive number, okay? Even 0, in which there is no relation to begin with. Okay, yeah, one more thing is that the relations have to be ordered, okay? In this example, you have the relationship between the student and the department, and the student majors in a department. So the first part of the relation has to be the student, and the second, the second part of the relation, that's the department, okay? If you switch the order and decide that the department majors in the student, well, that doesn't really make sense, does it? So order matters when it comes to relations. Next is the cardinality of a relation. Now, cardinality, according to the definition here, is the number of entity instances to which another entity set can map under the relationship. This does not reflect the requirement that an entity has to participate in a relationship. Okay, so let's start with one-to-one, okay? when it comes to one-to-one relationships, you have, let's say, an entity set X and another entity set Y. The relation is going to be one-to-one if and only if each entity in the entity set X is associated with exactly one entity in the entity set Y. Okay, what this means is that suppose you have some entity A in the entity set X and some entity B. Okay, 1 second. I'm rushing here because this is like my 5th take of this lecture. Okay. So you have an entity A in the entity set X, and you have the entity B in the entity set Y. Okay, these are specific entities, and suppose they're related. Now, it cannot be the case that after A is related to B, you can also have A related to C in Y. Okay, this is no longer a one-to-one relationship. That means given some A, you can determine exactly which B it's related to. And similarly, vice versa. Given some B, you can determine which A it is related to. Okay? This is a one-to-one relation. Next, we have the one-to-many relation, which says that each entity in an entity set X can be associated with multiple entities in the entity set Y, but each entity in the entity set Y is associated with at most one entity in the entity set X. Excuse me. Going back to this example here, the student has only one major, okay? In AURAC anyway. So the student majors in only one department or only one, major, but the department has many students majoring in it, okay? So this is our Y, the students, and this is our X, the departments, okay? Because each entity in X, each department can be associated with many entities in Y, many students, but each entity in Y, each student is associated with at most one department. See what that means? Next, many-to-many relationships, in which case each entity in X can be associated with many entities in Y and vice versa. In which case it's gonna be kind of hard to manage. So ideally you wanna try to stick to one-to-one relations, okay? Sometimes that's gonna be hard to do, so you can use one-to-many relations, but many-to-many you can avoid this fairly easily. Oh look, natural join. Okay, now here's a few notations for the cardinality. We're gonna use this one for the course, so you can completely ignore the other drawings here. The notation says here that, okay, when you have a faculty related to the class, this is a one-to-many relation, okay? Because one faculty member, a given faculty member, can teach multiple class sections, but a single section is taught by only one faculty member, okay? With the chairperson, this is one-to-one with the department, because each department can only have one chairperson, and each chairperson can only be chair of one department, okay? There are exceptions to this some places on Earth, but Finally, you have the student enrollment in classes, in which each student can be enrolled in multiple classes in a semester, and each class can have multiple students enrolled in it, okay? Now, this has the notation M and N, because usually you're not gonna have the same number here. Like one student's gonna have, let's say, 5 classes in a semester, but then each class has like 50 students in it. So using M and N makes it clear that the numbers are different in this case, okay? Relationship participation constraints. Okay, now we covered the degree and we covered the cardinality. Participation now talks about the minimum number of relationship instances that a single entity needs to be participating in. So we can have either partial or total participation, okay? When it comes to partial participation, given some entity set and some relationship, you don't need for all of the entities in that entity set to be participating in this relation, okay? So okay, we'll cover the example later. First, let's talk about total participation. When it comes to total participation, every single member of the entity set has to be a part of that relation, okay? Now let's go to the example. So you have the textbook entity, you have the class entity, and you have the faculty entity. And you have two relations, which are users and teachers, okay? We're not going to worry about the cardinality, so don't worry about it too much. Now, given a specific textbook, it may be the case that it's used in a specific class, or it may not be the case. So some textbook may not be ideal for a given class, or like may not be ideal for a class setting. They may be better for a different kind of use, or maybe the references or whatever. Okay, and similarly, a class may not use any textbooks, in which case they're not going to be participating. That specific class is not going to be participating in this relation, okay? So the class must have other kinds of readings assigned instead. For example, research papers, or websites, web pages, videos, and so on, okay? Or maybe even nothing at all. So that's your partial participation, which is represented by one line here, okay? Now, when it comes to the total participation, you're gonna have two lines. So here, you have the faculty member, which has partial participation because given a specific faculty member, it may be the case that this faculty member is not teaching a class in that specific semester. They may be on leave, sabbatical, whatever, okay? But when it comes to the classes, each class needs to have at least a faculty member teaching it, right? It doesn't make sense for a class to have no faculty members. Like, who's gonna direct the class? Who's gonna, like, assign the readings, tell people what to do? This is a university, we need guidance, right? And therefore, we need total participation here. To say that this relation, like, the class has to be participating in this relation. There has to be a relation between the class and some faculty member, okay? And there's an alternate relation notation rather than the single line and double line. You can have min-max, which is more detailed in a way, and it means that the min part refers to the minimum number of relationship instances that a specific entity is participating in, and the max refers to the maximum number of relationship instances that is participated in by a specific entity instance, by each entity instance, okay? Now, when the minimum is zero, this is partial participation, because for a given entity, it can be that they're not participating in any relationship instances, right? And for the min equal to 1 or more, the participation is total, which means that entity is participating in at least one relationship instance. Now, when it comes to the max, well, it's the greatest number of relationship instances the entity can participate in. Sometimes you use star for this rather than m or many, and that means no specific number, just a lot, okay? Now, here's a good example. So you have the student relation has major with the department, okay? A student may not have a major, in which case it's going to be the 0 here, okay? That's the minimum. So it's allowed, yes, that a student is not participating in the has major relation, okay? But they can participate in at most one instance of this relation. In this case, they're majoring in only one department, or yeah, okay? And when it comes to the department, it can be the case that a department is not participating in any relationship instances, in which case the department doesn't have any programs. So at AURAC, well, this year anyway, I'm not sure about 10 years from now, I think the department for math and science doesn't have any majors, if I'm not mistaken. I'm not really sure. I'm not about to go check the website now, okay? Like they don't have a math major or physics major or whatever. So that's going to be the 0 here, okay? Forgive me if I'm making a mistake. And it can also be the case that the department is participating in multiple relationship instances, in which case, multiple students are participating, okay? It kind of flips the script here, in which a student can be part of, a department has multiple students, okay? You need to focus on the fact that these are properties like relating to the relationship instances, okay? Focus on the relationship instances, not the actual entities participating in the relation, okay? Okay, next is the chairing here. So you have the department, right? Each department must be participating in the chair relationship, which means it has to have at least one instance, and also the maximum participation is 1, which means that it can only have at most one chair. Now, when it comes to the faculty member, a faculty member may be not a chair at all, meaning it's allowed that a faculty member is not participating in any of these relationship instances. And the most is that you have a single faculty member, for a given faculty member, you can have only a single relationship instance that involves that faculty member and some department, meaning they're only chairing one department, essentially. Okay. Next is this relation. So a department needs to be participating in this relation because the minimum is 1. And this means they're employing at least one faculty member, okay? And this is many, which means they're employing any number of faculty members. Can be a lot, okay? So the value of faculty members that they're employing can range between 1 to m. Next is the faculty side of this. So the faculty member needs to be employed by some department, duh, and they're only employed by one department, okay? That concludes this example. This is basically what I said, or at least part of it. Now, role I in a relationship, each entity has a function called its role in the relation. When an entity set is related to itself, we have a recursive relationship, like we said, and it is necessary to indicate the roles that members play in the relationship. Okay, so in this case, you can have that an employee is a manager of another employee in this recursive relationship, and vice versa. You can have that an employee has a manager that is also an employee, okay? This is what they mean by the role. So it can be the managed or the manager, or both, okay? This is generally not covered, but keep it in mind, especially for unary relations, okay? Also about the roles, same two entity sets can be related in different ways, okay? So a faculty member can be teaching students, in which case the faculty member has the role teaches, and the student has the role is taught by. And the faculty member may also be advising students, and students also need to be maybe advised by faculty members. Okay, try to work these out by yourself, what they mean based on the previous example, like this one. Good practice, I think. Okay, now moving on to the existence dependency. When an entity y or an entity in the entity set y is existence dependent on x, it means that an entity in y or entities in y cannot exist without a corresponding entity in x. Okay, in other words, every single instance or entity in the entity set y must have a corresponding instance of x. Okay, and if y is said to be existence dependent on x, then y must have total participation in its relationship with x. Okay, there's an example at the back here. Between the class and the faculty entities. Okay, the class entity is existence dependent on the faculty entity because you cannot have a class without a faculty member teaching it. And this is shown by the total participation here. Okay, and the slide actually says it as well. A class entity cannot exist unless it's related to a faculty member entity. Okay, so that concludes the existence entity. Now for the weak entities, this needs us to cover primary keys first. So this is where we go all the way back to the start and continue explaining. So yeah, this is from a previous take. Databases are composed of multiple tables, and the tables can have relationships between them. Some kind of relation. We'll cover that, what that exactly means in the later lectures. Okay, so the tables have multiple columns. Each column refers to an attribute, which is named like, at the start here, the header of the column. So we have multiple attributes or columns in each table, and we can also have, from here, multiple records in each table, okay? And the records refer to specific instances of the entity. So if this was a table students, then this is the second thing here, right one, this one. The whole row here is a single student with their own name, age, credit hours, and ID, let's say. This is a second student, this is a third one, and this is a fourth one. We just covered that. Domains are from a previous lecture. Yeah, the previous lecture, so we're not gonna repeat that. Records, we just explained these. Now, what are keys in databases? A key is an attribute or a set of attributes which helps you to identify a row in a relation, like a row in a table or a tuple in a relation, same thing. Okay, this definition is not really precise, but the point is that it allows you to like narrow down like what records you're referring to by a specific value of the key. And the point of that is to enforce certain constraints on the relation. Okay, we'll see what this means later exactly in the next lecture or two, I believe. No, just the next lecture, if I'm not wrong. Okay, and the point of this, as I show in the annotations here, let me remove them and start over. The way to do this unique identification thing is using super keys. Okay, this is a group of single or multiple keys which identifies rows in a table. Okay, The super key may have additional attributes that are not needed for the unique identification. So this is a set, okay? The curly braces here denote a set, and the set contains a single element, which is student ID. Now the student ID is unique for each student. You can't have two students that have the same student ID. Therefore, since this uniquely identifies every single student, we can say that this set by itself is a super key, okay? But any set of attributes that has this as a subset is also a super key. So you can see that this super key is only a subset of a larger super key which also contains the credits. And the credits are not needed for the unique identification, but they're still part of the super key, okay? Now let me remove the annotations here as well. Candidate keys. Candidate keys are a set of attributes that uniquely identify tuples in a table, same as we saw, except that you have no repeated attributes. Or alternatively, you have the minimum number of fields needed to ensure the uniqueness of the records that you're referring to, okay? And essentially, this tells us that, hey, credits here is not useful. So this whole set of two elements is not a candidate key, because the credits attribute here is not useful for uniquely identifying records. Only the student ID part is. Therefore, this thing here, the set student ID only, is a candidate key, okay? Now, a table can have multiple candidate keys, okay? It can have many different attributes, you can combine them in different ways, and that gives you the candidate keys, okay? Now, out of all the candidate keys, you select a single one to be the primary key, which is the main one that you use to uniquely identify the records, okay? Every table must have at least a single candidate key, otherwise it would be impossible to uniquely identify the records. A table can have multiple candidate keys, as we just said, but only a single primary key. Okay. Yeah, the rest is obvious. This is one of the main points, I believe, as shown in this example. Student ID by itself is a candidate key since it has no proper subset. Proper subset means a subset that is not equal to the original set, okay? So the only proper subset of this would be the empty set, and that does not uniquely identify entities, okay? There may be several candidate keys for an entity set. We saw that. Note that a candidate key can consist of a single attribute, as each of those do, student ID or national insurance number or social security number, or it can be a combination of attributes that by themselves, none of them uniquely identifies the attributes. Okay, now moving on to lecture 4, the relational model. The relational model basically relies on some mathematical stuff, which is the notion of a relation, in order to reason about, data and modeling data, right? The point of this is that, well, it's an abstract high-level model, and because in mathematics you prove theorems and so on, those theorems or knowledge of those theorems can be applied to your design of the database, for example, okay? And knowing those results and what you can do with the theory can actually help you design the database in a way that is more flexible, more, let's say, like in a way that lends itself to more interesting uses and applications in a way, okay? You can use expressive exact mathematical notation. We'll see more of this in lecture 6, same with these 2 points, so don't worry about it too much for now. Now the data structure. Relations on the implementation side of things can be considered as a table, and we have all these attributes, right? We already covered that much, but what needs to be clarified here is tuples. So you have these attributes, right? Each entry is a tuple. So a tuple basically means, so you have the couple, right? A couple means group of two. Triple is a group of three. A tuple means any n number, number of elements ordered, like, yeah, an ordered tuple. Okay, so this is an ordered four tuple or quadruple, where the first part is the record ID, the second part is this publication date, the third part is this author, and the fourth part is the title of the publication. Brad Pitt wrote that when he was 5, by the way, apparently, according to this database. Okay, so moving on, we're gonna skip this example for now and move immediately to the mathematical relations, okay? So given two sets, D1 and D2, their Cartesian product, denoted D1 times D2, is the set of all ordered pairs. So couples, right? Where the first element is from D1 and the second is from D2. And then the relation, a relation, is any subset of this Cartesian product. So let's look at an example first before we cover the other 2 points. Okay, suppose D1 is 1, 3, and D2 is ABC. The Cartesian product of these two sets is any combination of elements where the first element is in D1 and the second element is in D2. Any combination of two elements, like, okay? So you can combine 1 with A, you can combine 1 with B, you can combine 1 with C. You can also do 3 with A, 3 with B, and 3 with C, okay? And that gives you this set. And this set right here, denoted by the braces, as we mentioned before, is the Cartesian product of these two sets, okay? And then the relation, according to this definition, is any subset of this Cartesian product, okay? And that includes the entire Cartesian product as well. That also is a relation, okay? We specify which ordered pairs will be in the relation by giving some rule for their selection, okay? So we have the Cartesian product from the previous slide, and this relation R, also from the previous slide, is defined as follows. It is the set of all ordered pairs of the form xy, where x is in D1, y is in D2, and y is equal to A. So we need for the second element of the pair to be A. And that is true of exactly two elements of this Cartesian product, okay? And that gives us 1A and 3A. Now another example is the one where x is equal to 3, okay? And that gives us 3A, 3B, and 3C. So x here means the first element of the ordered pair. Okay, now let's go back here. You can form Cartesian products of three sets, okay? So rather than having just two sets, you can have D1 times D2 times D3. And then the relation would be any subset of the ordered triples formed, okay? So the triple would have like an element, let's say x, followed by an element y, followed by an element z, where x is in D1, this y is in D2, and z is in D3, right? You can also extend this to n sets, so you have an element of D1, an element of D2, element of D3, followed by an element of D4. And you can also have the same set actually, like d1 times d1. Then you'd have 1 1 1 3 3 1 and 3 3. Anyways, so here is the Cartesian product of three sets as an example, and that gives you 18 elements: 1 2 3 1 2 6 1 2 9 1 4 3 1 4 6 1 4 9. The point is that you're combining them in every possible way, where the first element is in here, the second element is in here, and the third element is in here. Okay, and then the relation would be any subset of this set. Okay, so using the rule thing that we just said, we can define a relation according to the rule that the third number be the sum of the first two numbers. Okay, so z equal to x plus y, and there's only two elements of this entire Cartesian product of 18 elements that satisfies this property. Okay, now let's go over this example. So you have four tables here. The first one is student, second one is faculty, third one is class, and the fourth one is enroll. Student has the primary key, student ID, and all of these values are unique, and you also have last name, first name, major, and credits. All of those are attributes. Then you have the faculty table, in which the faculty ID is the primary key. Then for the class table, you have the class number as the primary key. You also have faculty ID. Now this is the foreign key, which refers to this as the the primary key, like in the home relation. Okay, as we mentioned, I believe. No, we didn't mention it yet. Okay, so this is the foreign key of the foreign key faculty ID, which refers to the primary key of the faculty table. Okay, finally we have the class number foreign key, which refers to this primary key, and student ID foreign key, which refers to that primary key. Okay, now relation schemas. A relation schema, capital R, is a set of attributes A1, A2 through AN, and their domains D1, D2 through DN. Okay, so A1, let's say it's the name. The name would be some kind of string of a maximum length, let's say 30. A2 might be the age, then its domain, like the possible values it could have, could be an integer from 1 up to 100, and so on. Okay, now a relation small r on this relationship on this relation schema capital R is a set of mappings from the attributes A1 through AN to their domains D1 through DN. Okay, full stop here, by the way. R is a set of n tuples of the form A1 D1, A2 D2, and so on, up to AN DN, small d, such that small d1 is an element of the domain big D1, and so on. Okay, so the example here states that A1 is the student ID. Okay, A2 is the last name, and AN, in this case A5, is the credits. Okay, and then the relation is the set of all tuples that map student ID to an element of the domain D1, last name to an element of domain D2, and so on. So the first tuple here that we have maps student ID to the value S1001. Okay, second one, second part of the tuple maps the attribute last name to the value Smith in the domain D2, and so on up to credits being mapped to the integer 90. And this concludes the first tuple. And as we can see here, we have 7 tuples. Okay, Now, properties of the relations in terms of the relational model. The degree of the relation is the number of attributes. Okay, so this is a relation. Like this whole thing is a relation. And then these are all different elements of that relation, the tuples that consist that relation. Okay, the degree refers to the number of attributes. So this is a relation of degree 5. And then the cardinality of the relation is the number of tuples. So it would be 7 in this case. The reason for this definition is that relations are sets, as we saw here. This is a set. And in set theory, we call the cardinality, we refer to the size of a set by its cardinality, so the number of elements in it. So the number of tuples is the number of elements in this set, this relation. And that's why the cardinality refers to the number of tuples. Okay. Now, the intension, as we saw in the previous lectures, refers to the structure, the schema of the database. Okay. So unless you change the design of the database, the intension doesn't change. And therefore the degree doesn't change, because no matter what, your relation is still going to have the same number of attributes. Well, that specific table anyway. Okay. On the other hand, the extension refers to the database state, the elements that are in the, the values of the specific records at a specific time. And this changes all the time as you add and delete tuples or modify them. And therefore, the cardinality of the relation will change a lot. Okay, so when you add tuples, the cardinality is going to increase. When you delete them, it's going to be decreased. Okay. Next, relation keys. Relations never have duplicate tuples because they're sets. You can always tell tuples apart, implying there is always a key, which in the worst case is just the composite key formed of all of the attributes. But the point is they're always going to be unique. Now, in terms of relations, the super key is a set of attributes that uniquely identifies tuples. This is just speaking generally. The candidate key is a super key such that no proper subset of itself is also a super key, meaning it has no unnecessary attributes. And the primary key is a specific candidate key that you chose yourself. Okay. Finally, the foreign key is an attribute or combination of attributes that is the primary key of some relation, and that relation, as we said 3 slides ago, is the home relation. So the home relation of this is the faculty table. Okay, great. Moving on to the integrity constraints. Integrity refers to the correctness and internal consistency of the database. Okay. Integrity constraints refers to rules or restrictions that apply to all instances of the database. So no matter how the database's state changes, no matter what values it can have in the records, the constraints are always going to be met. The restrictions are always going to be applied. Okay. Finally, enforcing integrity constraints ensures only legal states of the database are created. That means the constraints make it so that given that you're in a legal state of the database, which means the values are valid, you cannot move from that state into a state where the database is legal, where the database is state, where the values in it are not valid. This is some formal verification stuff, so it's not really something you need to worry about. Just take it as general information unless you specifically want to study that kind of stuff for your own interest. Now, types of constraints. Domain constraints, in that you limit the set of possible values for an attribute. Entity integrity, which means that no attribute of a primary key can have a null value. Okay. Referential integrity, every foreign key must match the primary key of some tuple in the home relation or be completely null. So you can't have a so you can't have a foreign key that refers to a tuple that doesn't actually exist. Okay. Finally, general constraints or business rules. These are gonna vary from application to application, business to business, table to table, database to database. Okay. So just take them as general assertions. Now, representing relational database schemas. You can have any number of relation schemas. For each one, you list the name of the relation, followed by the list of attributes in parentheses. For instance, this is the name of the relation and the names of the attributes in parentheses separated by commas. And you can do the same for each relation or each table. Okay. And then you add, underline the primary key for each table or each relation. In this case, it's a composite key formed of these two foreign keys. Foreign keys are in italics, as you can see with this one and these two. And also, the foreign keys have numbers pointing to the original primary key that they are referring to. This is how the relational schema works. Okay. Now, types of relational data manipulation languages. Okay, let's just read this. The procedural ones are prescriptive, which means the user tells the system how to manipulate the data. For example, relational algebra. The non-procedural ones are declarative, which means the user tells the system, the language, or uses the language to say what data is needed, not how to get it. For example, the relational calculus and SQL. Okay. Other types are graphical, fourth generation, which is user-friendly stuff, and natural language, which is the fifth generation, using a restricted version of language, English or some other natural language. Okay, last two slides, I think. Yes. The object-oriented model is an alternative, I guess, for the relational and the entity relation model. You don't really need to worry about this too much. This is mostly OOP stuff that you should have taken in that course. It's a prerequisite to this one after all. Let's just read this as well. The object-oriented model is primarily a semantic model. It's based on the notion of an object, which, like an entity, is a representation of some person, place, event, or concept in the real world that we wish to represent in the database. While entities have only attributes, objects have both a state and a behavior. Okay? The state of the object is determined by the values of its attributes, which are also called instance variables. The behavior of the object is the set of operations or methods that are defined for the object. And a class is similar to the entity set, and it consists of a set of objects having the exact same structure and behavior. And you can represent that using UML. But this is complicated and usually not really, maybe too far away from what we're doing. So it only gets 2 slides of coverage. Okay, that concludes this lecture, I suppose. Moving on to lecture 5, which is mapping the ER model to the relational model. So we're going to go from diagrams to tables and columns and rows. Now, this is just a review of what we did in the previous lecture, so you can just ignore it. Okay, so when it comes to converting the ER diagrams to tables, roughly speaking, we're going to first make a table for each entity set, in which the columns are the attributes of that entity set. Okay, and the primary key is still the same primary key. And in addition, when it comes to the relations, you might make a table for a given relationship, or you might not. It depends on the type of relation, and we'll see that in a bit as well. So here are different types of components in ER diagrams. Each one gets a specific treatment in this conversion. I promise it's all intuitive, but you'll have to take a look at it and think through it yourself. We're going to go over the regular, also known as strong entities, weak entities, one-to-one relationships, one-to-n relationships, many-to-many relationships, multi-valued attributes, and n-ary relationship types. Okay. So here's the first type, which is the strong or regular entities. So we have an entity student here on the left, which has 4 attributes: SID, name, major, and GPA. And this one is the primary key. We're just gonna make 4 columns here. Okay. First column is, in this case, the primary key, which is the same primary key as in the ER model, ER diagram. And then you have the other attributes as their own columns. And then for the professor entity, same deal. You add the 3 attributes and make one of them the primary key according to whichever one was the primary key in the ER diagram. When it comes to weak entities, you're going to also make columns for every attribute of the weak entity. But you're also going to add a column for the primary key of the strong entity associated with this weak entity. Okay? We'll see an example in a bit. So, yeah, the primary key of the weak entity is going to be the primary key of the associated strong entity, which is this foreign key, plus a discriminator, which basically says, yeah, given all of the weak entities associated with a specific strong entity, this is going to be an attribute or group of attributes that uniquely identifies them among the entities associated with that specific strong entity. Okay, that was a bit of a mouthful, so let's look at an example. So we have a weak entity, children, and a strong entity, student. The weak entity is going to have 2 attributes here, age and name, and these are going to be columns here. But we're also going to add a column for the primary key, in this case a foreign key, of the student that is associated with that child. Okay, so we have, in this case, 2 entries, and the primary key of each entry is going to be the name of the child plus the student ID of the you know, the parent of that child. Okay, so we can have multiple children with the same name, but only one of them like they're not gonna have the same parent. Okay, like who names their children the exact same name, like multiple of their children the exact same name? That doesn't make much sense, does it? So that's the point here. It's enough after you've narrowed down which parent it is to have the child's name as a discriminator. Here's another example. So we have the strong entity account, which has 2 attributes, account number and balance. And you have the associated weak entity, which has its own 3 attributes, transaction number, amount, and date. Now, because this is a weak entity, you also need to add the primary key of the associated strong entity, which is the account number. And that's why we're going to have these 4 columns here. The transaction number, date, and amount are the original 3 attributes, and the account number here is going to be the primary key from the associated strong entity. Moving on to the relations. So you have one-to-one relations, And first type is going to be the one-to-one relations without any total participation. In this case, you're going to make a table, okay? An additional table for that relation. It's going to have as columns the primary key of the first entity and the primary key of the second entity. And if the relationship has its own attributes, then you might add a third or fourth column for any of those attributes, okay? Next, when it comes to one-to-one relations with one total participation, then you're going to use the foreign key approach, in which the entity with the total participation is going to have as a column the primary key of the entity without total participation, which is the case in this example. We have a column here for the primary key of the entity without total participation, okay? Because not all students have children, but all children have an associated student as their parent. Finally, when you have two total participations, so total participation on both ends, then the two entities as well as the relation are all going to be merged into a single table. Okay, so rather than having a table for entity 1 and a table for entity 2, you're just gonna have a big table like that. And this part is the, let's say, the part of this table. And you're gonna have a second table for the second entity, okay? So rather than have separate tables, you're not gonna do that. You're just gonna have one big table, because this is one-to-one with total participation. So it's more efficient to just make it a single table. And on top of that, you're gonna have any attributes for the relation, okay? That's the merged relation, or also known as the alternate mapping. So here's an example of the first approach, in which we have partial participation on both ends, and then the foreign key approach, which has one total participation and one partial participation. Here's another example. We skip that. Now, when it comes to one-to-many relations, again, we can have no total participation, or we can have a total participation on the end side, okay? When it comes to the one without total participation, we're going to use the relationship relation again, which means making a new table and adding columns for every participating entity's primary key. This is enough. Now, when it comes to this, you're going to go to the end side and you're going to add a column there. And what's in that column is a foreign key, which is the primary key of the other entity. Let's see an example here. So we have total participation on the end side, okay? What we're gonna do is we're gonna add on the end side, on the student table, we're gonna add an additional column for the primary key of the associated of the entity on the one side, the professor side, and that's this column. And you're also gonna add any attributes that the relationship has, in this case the semester. So you're gonna add that also as an attribute. Again, we're trying not to make many tables and many redundant things. So this is more efficient to just have as a single table the student and like the name of their, or the ID of their advisor, and what semester they're advising them in. Okay. Skip that. Now, when it comes to many to many relations, it's not possible to use the foreign key anymore, and you're gonna be forced to make a new table. And once again, it's gonna be the same deal, entity 1 with entity 2. Okay. When it comes to n-ary relations, as is the case here, so you have this entity set, a third one, and a fourth one, and they're all related together. In this case, you're just gonna make a big table rather than just entity 1, entity 2. You're gonna have also entity 3 and 4, and possibly more in the case of like bigger n-ary relationships. Okay. What else? Yeah, the point of us doing all of this instead of making just relations all the time is to reduce redundancy as much as possible. We want to try not to store the same data multiple times. Okay, and the reason for that is sometimes like there's no point. You're not gaining any additional benefit from doing that. Okay. When it comes to composite attributes, like the address, which has two components, the street and the city. In such cases, you're gonna add the street and the city as attributes, and you're not gonna have a separate address column. Okay. When it comes to multi-valued attributes, like for example, if a student in the database has several emails and you want to store them, what you're gonna do instead is to make like a separate table where you have two things. First is the primary key of the student, okay, and the second thing is their actual email, okay. And so you're gonna have multiple entries where, let's say, student 1 has, let's say, their Outlook email. Student 1 again is gonna have, let's say, their personal email, and then a third, let's say, again, one more thing is that they have a third email for some purpose, and then you're gonna have like a second student with their own emails. Now, when it comes to the student table, you're not actually gonna add anything new there, okay? It's not necessary because this has all the information needed, okay? So as we can see, you have the student ID, name, major, and GPA. No mention of the degree table whatsoever. And then you're gonna have here a column for the associated, for the student primary key, as well as the degree they're holding. So the student has 2 degrees, which are FSC and BS, and the student has 3 degrees, which are BS, MS, and FA. And yeah, again, there is no column here saying explicitly like the student's degree. Instead, we're gonna look at the degree table and check which entries have the student ID equal to, let's say, 1, 2, 3, 4. Okay. That more or less covers everything, I think. So here's a bunch of examples and a summary. If you want to read that, I'm not gonna bother. And that concludes this lecture. Moving on to lecture 6, which is on the relational algebra. So this is kind of a mathematical foundation, a theoretical foundation for data manipulation languages, such as, most of SQL, let's say. And the idea here is that you have your database, right, with multiple tables, and you want to get specific data from that database, satisfying specific conditions, and present it in a nice format, okay? This is the entire point of the relational algebra, and it's something called a query. So a query, it's kind of it's an operation that you specify, and you input this operation into, let's say, SQL, given correct syntax, of course, and the database management system is gonna parse that query and return you like a list of records that satisfy the conditions that you want in the format that you want, okay? Now, the relational algebra has three fundamental operations. The first one is selection, the second one is projection, and the third one is the Cartesian product. Okay? I'm sorry, something just came up to update. Classic Windows, man. Anyways, so you have selection, projection, and Cartesian product. You also have multiple types of joins, and joins are actually just a specific type of combination of these three operations, okay? Outer joins are also included in that. And then when it comes to the aggregate functions, these compute a summary of information, for example, the sum, count, average, minimum, maximum, whatever. Now these are not quite theoretical things like these, but they're also useful in getting like specific information out of the data. Remember from lecture 1? Okay, so the examples in this lecture are going to be based on this database that we already looked at. So just keep that in mind, may be useful for the examples. First operation, like we said, is selection. What it does is return only the records in a specific table that satisfy a specific condition, okay? And there are two ways to write this. The first way is the SQL-like syntax. You have select, where, and giving, okay? And the second way of doing the notation is the mathematical one, which is the main focus of this lecture, okay? You might not have to know this right now for the midterm, let's say, but this you definitely need, okay? So the basic syntax for this one is select, where, and giving keywords. And then here you write the name of the original table that you're going to be operating on. Here you're gonna write the condition, which is the way you're gonna select the records, like what condition do you want them to satisfy, such that when the condition is true, the record is going to be returned in the result, and when the condition is false, it's not going to be returned in the result. And then you have giving the new table name, which is like, yeah, it puts the result into a new table, at least a temporary one anyway, I'm not really sure. And this part, giving new table name, is optional, okay? So I don't have to write this. The important part is select table name where condition. Similarly, for the mathematical notation, you have sigma, and this just means select, okay? In the subscript down here, you have to make it a little lower, and you have to make it like smaller text, let's say. You're gonna write the predicate, which is just the condition, same thing, okay? Then you're gonna put parentheses and the name of the original table that you're operating on. Finally, if you want to put the result somewhere, you can do the new table name equals. The square brackets are not part of the notation, okay? So as you can see in the example here, result equals sigma student ID subscript student ID equals S1013 parentheses student, okay? The selection, in short, just gives you all the records that satisfy a specific condition. It's not that hard. We already explained this. For the condition generally may be composed of several like smaller conditions. You have less than or equal to, greater than equal to, not equal to. These 6 form like the basic, let's say, atomic conditions. And then you can group the conditions using and, or, and also not. This isn't really grouping, but it's also true. Okay, so major equals math in this example. By the way, one second. This needs a quote here. They forgot to put it. Okay, so major equals the string math and credits greater than 30. This is going to return all the records in the table student where the student is a math major whose credit hours exceed 30. Okay. Alternatively, in the SQL notation, you can just use and. Okay. It's much easier. So that's it for the selection. One more thing I need to mention is that you can also put parentheses here, okay? And that's basically it. Okay. Next is projection, where so you have a table, right? And it has all these different attributes. Let's say 3 attributes. And projection basically removes some of those attributes, some of the columns, okay? So let's say you want only this column. You're going to, okay, let's say this is called A1, okay? You're gonna write pi for project. Then in the subscript, you're gonna write the names of all the attributes you want to keep, okay? In this case, it's just A1, okay? Then you're gonna put parentheses, and let's say the name of the table is T, okay? Now, if you wanna keep two attributes, or let's say you wanna keep okay, two attributes, but let's say we wanna keep this one and this one, okay? Let's say this is A3, okay? Then you're gonna write here, comma, A3, okay? And that's gonna return basically a new table with just okay, that's just bad, man. 1 second. Okay, A1 and A3, okay? And one more thing to note is that okay, it's not mentioned here, but identical records after projection are going to be discarded, okay? So let's say you have here you have 1, 2, 3, and you have 1 that looks like a 2, but let's say it's 1, okay? I need an actual pen, not a touchpad. Okay, 1, again 1, and this time you have 1, 3. So these two records are completely different, right? Now, after you project, you're gonna remove this. So you're gonna have 1, 3 and 1, 3. In that case, the duplicate is going to be removed. You're only gonna have a single copy of 1, 3, okay? So just bear that in mind. The projection will leave you either a table with the same number of records, assuming that there's no duplicates after the projection, or if there are duplicates, as is the case here, then the cardinality of this table is going to be smaller than the cardinality of this table, okay? That's basically it for the projection. It just, you cut columns and you remove any duplicate records after that, okay? So you write pi, in the subscript you write the list of attributes separated by commas, and then in parentheses you write the name of the original table or the original relation, okay? Yeah, the project operation removes any duplicate tuples because the result of the project operation must be a set of tuples, and mathematical sets do not allow duplicate elements. So let's say this set A, so it has two elements supposedly, A and A, right? Wrong. It's actually just the exact same thing as the set containing only one element, which is A. There's a thing called multisets in which they would be two different sets, but we're not covering that at all, so no need to confuse you. Okay, Next, yeah, the notation for the project operation. When it comes to the SQL-like syntax, you're gonna have the project keyword, the over keyword, and possibly again giving, okay? Now, here, you're gonna have the name of the original table. Here, you're gonna have parentheses and the names of the different columns. And possibly, you're gonna write giving the name of the new table, okay? Yeah, we mentioned this already. The number of tuples in the result of the projection is always less than or equal to the number of tables in the original relation. And if the list of attributes includes a key of the relation of the original table, then the number of tuples in the result of project is equal to the number of tuples in R, because they're uniquely defined, right? And the key is still there to uniquely like distinguish between the different records. Therefore, it's impossible to have duplicate records, and because of that, none of them are going to be removed. Projection is not commutative, which means that if you project onto, so if you have project onto, let's say, column A1, and then this is actually applied on the result of a different projection, which is A2, and this is applied on the original table. This is not always the same as if you did pi sub A2 first, and it was done on the result of pi sub A1 of t, okay? The reason is because the removal of duplicates, duplicate records is not going to be always the same, okay? Easy enough. Oh, and one more thing. Forgot to mention this. Selection is commutative. So you can apply it in any order and you're gonna get the exact same result, okay? Okay. This is a couple of examples. So you have a table of students, right? Here we have 7 students of different IDs, last names, first names, majors, and credits, okay? You project this table onto only the majors column, and it's going to basically just return you a set of majors, okay? And there's not going to be any duplicates because that's not really necessary information, right? Okay, so you're gonna have only 4 records in here. Then if you project class over the faculty ID and the room, then you're gonna get this table. And let's take a look at that. Class over the faculty ID and the room, okay? This guy only teaches in one room, so you're gonna have this record either way. Then this guy teaches in both rooms, sorry, in the same room for 2 different classes, as we can see here. Therefore, once we project, we're not gonna have this or this to distinguish between the 2 classes. We're only gonna have F105 M110 and F105 M110. Therefore, this is a duplicate and one of them is gonna be removed, okay? Which one doesn't really matter. This one only appears once, so it's fine. And then for this one, once again, it appears twice, F110 H225 and F110 H225. Therefore, again, it's going to be, yeah, it's gonna remove the duplicate. Therefore, we only have 4 entries in the new table, okay? And yeah, you can have, as we already hinted at kind of here, you can apply a relational operation on the result of another relational operation, okay? Moving on. Okay, Either we can write the operations as a single relational algebra expression by nesting the operations, and that's what I did here, or you can apply one operation at a time and create intermediate result operations relations. And this is as is done in this example. They do this selection and they put the result in temp, and then they take temp and use it as the original table in the project operation. Okay, this is the only real way of stringing of combining relational operations in this kind of textual syntax. But when it comes to the mathematical one, you can just have this parentheses here, and this is going to be applied on by the project operation. Okay. Next thing is the product operation. This operation is used to combine tuples from two tables in a combinatorial fashion. It's denoted by A times B. Okay. And A has, keep in mind, A has this many attributes and B has this many attributes, right? The result is going to be a table with all of these attributes together. So you're going to have A1, A2 through AN, as well as B1, B2 through BM, as is shown here. So this is a table with all of these different attributes, okay? And the records in this table are going to be formed by concatenating all rows of A with all rows of B, okay? So what this means, so suppose you have the student and enroll tables, okay? You're gonna have every possible concatenation of the rows. So on the left here you have the student part, and on the right here you have the enroll part, okay? Now concatenation of the tables means of the records, of the rows, whatever, means that for every record in student, you're gonna concatenate it with every record in enroll and insert all of those combinations as records in the student times enroll table, okay? So you have 9 entries in enroll, so you're gonna have 9 entries starting with the same record from student and ending with a different record from enroll. So you're gonna have this guy with the first enroll, same guy with the second enroll, and so on. Now notice that we're allowing the combinations to have like different student IDs and so on. And also notice that enroll.studentID and student.student ID. Like these two attributes have the same name, but to distinguish between them and where they came from, we're gonna add like the table name as a discriminator. Okay, so you had 7 records here and 9 records here. So 7 times 9 equals 63, right? And that's going to be the number of columns here, rows here in total. So every possible combination, where the first part of the combination is from the first table and the second part of the combination is from the second table, okay? Now, what's the point of this? There's actually not much benefit to the Cartesian product itself, okay? Now, here's what you're gonna do. You're gonna create this product, and then you're gonna select only the rows where the student IDs match, okay? So you're gonna select this row, like these two rows, because the student IDs are the same, right? S1001, S1001, okay? And you're gonna also select the ones where you have S1002 and S1002, which is some rows that appear here, 3 of them to be exact, okay? And so on. And when you do this, when you first do a product followed by selection, just in general, that's called the join operation, okay? And this is denoted by theta. Okay. The sequence of Cartesian product followed by select, just any select. It doesn't have to be that these two are equal. It can be any kind of condition, okay? This is called a join, okay? This operation is very important for any relational database with more than a single relation because it allows us to combine related tuples from various relations, okay? So Cartesian product gave us a way to combine tables in general, but in order to make the generated table useful, you're gonna use selection, okay? And because you do this so many times, you might as well make it into a single operation, and that's called join, okay? The notation here is A, then this weird looking thing, and then a condition, okay? And the condition here is denoted by theta, okay? Then B, okay? Alternate notation, is that you do a selection with the join condition, whatever it might be, applied on A times B. Okay, so this is the one that you already kind of know. It's a Cartesian product followed by a selection given some condition. Or alternatively, you can do this kind of shortcut where you have this X looking thing with like the lines on the right and left side, which is written like this in ASCII because you don't have this kind of weird symbol in ASCII, and subscript the condition. Okay. Usually, you can just go for the sigma notation. It doesn't really matter. So, sigma subscript credits greater than 50 of the thing student times enroll. Okay. And this is going to return all the records. Okay, not this one. It's going to return all the records where credits is greater than 50. And this still has the problem that the student IDs may be different. That's totally fine. This is not the goal in this example. But when you do want that, and it is most likely the case, it says here the most common use of join involves using join conditions with equality comparisons, okay? And this is called an equijoin. Let's read the slide. In the result of an equijoin, we always have one or more pairs of attributes whose names need not be identical that have identical values in every tuple. When the theta is equality on the common columns, we have the equijoin of tables. Okay, so the kind of precondition, let's say, of the equijoin, like the assumption of the equijoin is that the two tables that you're applying it on have a column that is shared between them, okay? This needs to be the case. If it's not, then equijoin is not defined at all, okay? So you're gonna combine, let's say, yeah, you're gonna compare. Sorry, I was reading this. You're gonna compare every tuple of the first table with every tuple of the second table, and join only the ones where the values in the common columns are equal. So in this case, we have student ID and student ID, right? The name here is the same, student ID. Don't worry about the discriminator, student or enrolled, okay? You're gonna compare this with this and see, are they equal? Yes, okay, select it. And the result of the equijoin gives you this table, okay? So the equijoin is gonna select this row is going to select that row. It's not going to select this row. It's not going to select this one, nor this one, or any of those, or this one. It is going to select this one though, because S1020 is S1020, is S1020. Okay, so that's the equijoin. Necessarily, the column has to be shared between the two tables, okay? Otherwise, it's not really defined, at least in this notation. But if you're going to be more verbose, then you can specify student.studentID equals enroll.studentID, okay? But when it comes to student equijoin enroll, it's kind of implied that that you're assuming there already are columns that share, that are shared between the two tables. Next, we have natural join. So after you have equijoin, so you have two columns, both of them are student ID, and because of the equijoin, because of what you did, you set them equal to each other, right? So what's the point when all of the values of these two attributes are going to be the same in every single record? Just remove one of them, right? So first you did the Cartesian product, and then you selected only the rows that have these two values the same. And now you're gonna project over all of the columns except this one, okay? So we combined all three fundamental operations to form what is called the natural join. And it's another variation of join in which the repeated column is eliminated, because there's no point in having two copies of the same column, considering all of the values are going to be the same, right? And that's the natural join, and it's denoted just this, no subscript, okay? We also have left semi-join, which is denoted like this, and right semi-join, which is denoted like this. And it projects it, basically it does the equijoin, or natural join, doesn't really matter, both of them are valid. And then you project it onto only the attributes of A. That's for the left semi-join. For the right semi-join, you're going to project it onto only the attributes of the second table B, okay? As shown here, student times student right semi-join and enroll. And this is basically just the enroll table, the attributes of the enroll table, sorry. Okay, so we have now the operations from set theory, starting with the union. The union, given two sets, gives you a new set, which is formed of basically taking all the elements of R, or all the elements from S, and putting them into the same set, removing all of the duplicates, okay? So let's say S union R is the set of all elements A such that A is in S, or A is in R, okay? And because this is a set, mathematical set, you're not gonna have duplicates in here, okay? Next, when it comes to unions as well as intersections and set differences, in relational algebra, you can't just throw in together elements from two different sets. You need to also specify that the sets have compatible attributes, okay? The relations. So you need to specify two things. Firstly, that the number of attributes is the same. So n here is also used here, okay? If they didn't require that, they would have used n and let's say m, okay? But because they used n and n in both cases, that means these two numbers must be the same, and that means we're specifying a condition kind of that the number of attributes is the same for both relations, right? Okay. The second condition is that the domains of the corresponding attributes are type compatible, okay? So A1 must have the same domain as B1. A2 must have the same domain as B2, and so on up to Bn, okay? The resulting relation for R1 union R2 has the same attribute names as the first operand relation R1. And this is just a convention, it doesn't really matter. Okay. The intersection is denoted this way, as you know, and it includes all the elements that are in both sets, okay? So if this is R and this is S, then this part in the middle here, this is the intersection of R and S, okay? And again, you have this type compatibility issue in which they need to have the same number of attributes and the domains of each corresponding attribute. So A1, B1, A2, B2, and so on. The domains must be the same for each pair of attributes. Finally, we have the set difference. So you have R and S. This gives you the set of all elements of R, so R minus S gives you all elements of R that are not in S, okay? And that's obviously going to remove the intersection. So you're gonna have this set as the result of the set minus, which is R minus S, okay? Don't worry about these elements, they're not there in any case. The point is all elements of R that are not in S, okay? The elements here weren't elements of R in the first place, so you don't even need to consider them. Okay. Intersection, wait. Yeah, okay. I pressed left arrow key. Now, the idea should be clear by now, but let's go over a couple of examples. Okay. So first we have just two relations, two tables, and they're union compatible because the first attribute here and the first attribute here are both strings, and the second attribute here and the second attribute here are both also strings, okay? So they have the same domain and they also have the same domain, these two pairs, okay? So first we take the union, student union instructor. You have Susan Yao, Ramesh Shah, and this guy appears in this table again, and she also appears in this table. So you have these two duplicates, okay? They do not appear more than once in the resulting table because this is a set, okay? I think there is no other repetitions. Yeah, no. So the total cardinality of the result is going to be the cardinality of this plus the cardinality of this minus the cardinality of their intersection, okay? Because we're gonna add all of them and then we're gonna remove the duplicates. Okay. And the duplicates are those that are in the intersection, and that is shown in this table C, okay? Student intersection instruction gives you the instructor gives you these two elements. Then we have student minus instructor. So the set of all students that are not instructors, let's say, okay? And that's going to return the student table minus the entries that are also in the instructor table. So you're not going to have this one nor this one anymore, only these 5 elements, hence this, okay? And the cardinality of this is going to be equal to the cardinality of the original table minus the cardinality of the intersection. Finally, you have instructor minus student, which goes the other way around. So you're going to take this and you're going to remove the intersection. So you're going to remove this one and this one. And that gives you these remaining 3 tuples. couple of exercises here, followed by a summary. Okay, so let's solve them. We have a selection applied on the employee table. Oh, I forgot to remove that. It's from a previous take. Okay, so you have the employee table. You apply a selection where the last name is Adams, and then you do the natural join with the assigned table. Okay, so the assigned table is already given. We don't need to do anything with it. Then we're gonna select the entries here that have Adams, obviously only one. So you're gonna have like that, employee ID and last name, you have E110 and Adams, right? Okay. Now you're gonna natural join this with the assigned table. Okay. Now there is an attribute that is shared between these two tables, which is employee ID. So you're gonna extract, so you're gonna do the Cartesian product, and then you're gonna select only the rows of that Cartesian product that have the employee ID here equal to this employee ID here, which is E101. Okay. Therefore, you're gonna end up with 5 columns. First one is the employee ID from the employee table, then the last name from the employee table, then the employee ID from the assigned table, followed by the project number, and finally the hours. Okay, and this is just an equi-join. Okay, and this has 2 entries. Both of them have employee IDs 1001 and 1001, sorry, E101, and this one also has E101. Now, this is a natural join, not an equi-join. Therefore, we're gonna just remove one of the duplicate columns, let's say this one, and we end up with a table with 4 columns, okay? And that's the result, basically. So, a table, 4 columns, 1, 2, 3, 4. Then you have the employee ID, last name, project number, and the hours. And you have 2 entries. The first entry has E110. Oh, my bad. Not E101. It's E1110. Okay. So you're going to have first E110, then the last name Adams, followed by P15 and 700. P15, 700. Second entry is going to again have E110, Adams, P20, and 350 hours. Okay, that's the result of this operation. Now, the second one is you select all the projects with a budget greater than 400,000. You natural join that with assign, and then you project that over only the employee ID. Okay, let's break it down. So, budget greater than 400,000. So you're gonna take 2 entries. First one is this, and the second one is this one, right? So let me just cross that out to make this easier for me, instead of having to draw the new table all over again. Then you're gonna natural join this with the assign, okay? And the assign, let's see, the shared attribute here is project number, okay? So you're gonna look at the rows that have the same project number in both of them, in both tables. In this case, you have P10 with P10, P10 with P10 here, and P10 with P10. Sadly, this has nothing. So you're gonna end up with 3 let's say 3 entries in the natural join, because this doesn't have any equal things in equal corresponding records here, so we're just not gonna count it. Okay, it's not gonna be a part of it because the condition is not satisfied. There is no record that has P23. So P10, 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 all of those are going to be in the as records in the new table. So you're gonna have employee ID, project number, hours, project name, and budget. Okay, again, natural join, so we're not gonna take the duplicate column. I just showed you that the first time just to like get the idea across, like the difference between equijoin and natural join. Okay, so you have employee ID, this is employee ID, you have project number here, you have hours here, you have project name, and you have budget. Okay, you're gonna have budget greater than 400,000. In this case, it's going to be okay, let's see, 3 records. All of them are the same project, so you're gonna have project number equal to P10 in all 3 cases here. This one are also P10. Project name is going to be Hudson in all 3 of them, and the budget is going to be 500,000 in all 3 of them. Okay, and then for the hours, you're gonna have 200, you're gonna have 400, and you're gonna have 300. Okay, for the employee IDs, you're gonna have E101, E105, and E115. Okay, I'm not gonna bother writing those ones, so yeah. Finally, you're gonna project over the employee IDs, which is going to remove all of the other columns. The result is just this single column with E101, E105, and E115. So that's the result of this operation. Okay. Summary: relational data manipulation languages may be procedural, non-procedural, graphical, fourth generation, fifth generation. Did we see this? I remember seeing it in like a previous lecture or something, but not this one. I'm not really sure. It doesn't matter. Relational algebra is a formal procedural language. Its most commonly used operations are select, project, and natural join, and join being just product followed by select. Many other relational algebra operators exist, such as union, intersection, and difference. And this is definition of the select, project, and join, which we've already seen. That concludes this lecture. Let me see how long it took. I think 45 minutes across two videos. So yeah, it's a long one. Okay, to wrap things up, I want to go over the exercises or class activities that were released by the doctor last night, I think. So, oh, this is highlight, not drawn. Okay, there we go. So, the questions in the midterm, we're gonna have at least 3 that are guaranteed to come. The first type is going to be translating a verbal description like this one into the entity relationship model, okay? And this is going to be the diagrams, as we can see here, with the rectangles, the ovals, and the diamonds, right? Now, the second type of question is going to take one of these and transform it into the relational model, which is given by the tables down there, okay? So this is these activities are kind of like doing both steps at once, okay? So covering 2 types of questions at once. The third type of question is going to be relational algebra stuff, which is covered in one of the class activities. I'm not sure yet if I have the time to go over that in the recording. I mean, it's already the day before the exam, literally. So I'll do as much as I can and just upload whatever I have by the end of the night, okay? So the question says here, a supplier processes many purchase orders and sells a number of products, okay? The keys are already provided, supplier number, purchase order number, and product number, okay? And this is kind of an indication that, hey, this is an entity. So we have three entities now: supplier, purchase order, and customer, okay? Sorry, product. Let's continue reading. Each of the purchase orders that a supplier may process includes several products. The relationship between order and product is defined as line item. And finally, a customer number may place one or more purchase orders. A purchase order may be placed by only one customer. So we have a fourth entity, customer, okay? I did all that reading just for that. Next, we're going to cover the relations. So, the attributes. So here we have the supplier ID. This one has the product purchase order number. This one has the product number. And this one has the customer number, okay? Now, the supplier processes many purchase orders. So let's say this is the supplier and this is the purchase order. So we're going to have a relation, which is processing, right? And we're going to have this as one and this is many, okay? Okay, this looks terrible, but as long as I'm saying what it is, it's fine. Okay, a supplier processes many purchase orders. So we have, for each supplier, they're going to process many purchase orders, and each purchase order is associated with only one supplier. Obviously, you can't order from two suppliers at once. Okay, next. The supplier also sells a number of products. So we're gonna have a relation. Let me take it all the way down here because I know there's gonna be a relation around like this area. So this is sells and this is product, okay? Now, the supplier sells a number of products. So once again, we're gonna have many here because each supplier is associated with many products, okay? Also, a product is sold by only one supplier. So for each product, there's only one supplier that is associated with that product, okay? Next, each of the purchase orders that a supplier may process includes several products. Each purchase order contains several products. Therefore, this is a one-to-many relation between the no, sorry, it's not one-to-many, but the product side is definitely many, okay? So we have a relation here between the purchase order and the products, and each purchase order has many products possibly, and each product can also appear in multiple purchase orders. Therefore, we're gonna add an n here, also meaning many, okay? But not necessarily the same number as this. That's why we're using a different symbol. If it was always the same, let's say 5 to 5, 4 to 4, whatever, then we'd be writing m here. Okay, so the relation between the order and the product is defined as a line item. So here you're gonna write line item. Now, a customer may place one or more purchase orders. So we're gonna have a relation between the customer and the purchase order, and each customer is associated with possibly many purchase orders, okay? a purchase order may be placed by only one customer, so each purchase order is associated with only one customer, and therefore we put a 1 here. Okay, and that's the entire entity relationship diagram for this question. Don't worry about this one, it's only relevant for the second part of the question. Okay, otherwise everything else here is the exact same as what we just drew. Okay, now we're gonna convert this to the relational model. First, we create a table for every entity here. So we're gonna have a table for the supplier, and this is going to have, at the very least, the supplier ID, followed by whatever other attributes there might exist. Doesn't really matter, we don't care. Okay, and then we're gonna have a table for the purchase orders, which are at least going to have the product number, purchase order number, so that's going to be this one. And we're also going to have the product number for the product table. So we're going to have the product table, and let's say this is the product number. Okay, we also have the customer table, say like this. Okay, and all of these have their own attributes that are not related to the specific task here. Okay, now we have a one-to-many relation between the supplier and the purchase order. When you have this and it's let's say total participation, okay, then you're gonna add the supplier ID, primary key, as a foreign key in the purchase order table. Okay, so here's a purchase order table. You're gonna have supplier ID in here as a foreign key. Okay, plus whatever other attributes there might be. Then we're gonna cover this relation, okay, between the customer and the purchase order. Now again, obviously this needs to both be total participation, because a purchase order cannot be associated with no customers, and the customer okay, may place, so we keep that as partial. Okay, so again, we need to add another attribute to the purchase order, because each purchase order is associated with one customer, right? So that's going to be our third attribute here, and there might be fourth one and fifth one and so on. So let me just add that as an extra, whatever might also be in the purchase order. Next, for the relation between the supplier and the product, once more, this is a one-to-many relationship, and therefore we're gonna add the primary key of the supplier as a foreign key in this guy's table. Okay, so I think this was the product table, so we're gonna add supplier ID here, and that's it. The final relationship is going to be this one. Now when it comes to many-to-many relationships, you need to make a new table. Okay, so here's our fifth table. Let's say it's called line item, as given by the question here, and it's gonna have two attributes only, because the line item doesn't have any extra attributes in this case. The first attribute is going to be the ID of the purchase order. The second attribute is going to be the ID of the product. Okay, so here's the purchase order number and here's the product number. Let's look at the solution now. The supplier only has its own ID. Purchase order has the ID of the supplier that is processing it, as well as the customer that placed the order. The line item is going to have the the purchase order number and the product number. If there are attributes, well, despite what I just said, if there are other attributes, we're gonna add them, but if not, it's fine. Okay. The product, since it's related to each one's related to exactly one supplier, we're gonna add that as a foreign key here, and also add the primary key, which is a product number, obviously. Finally, for the customer, we don't need to add any foreign keys or whatever, so we just put the primary key and any extra attributes such as name or whatever. Okay, so that concludes the first question. Second question, an airplane tail number is assigned to several flights. A flight is assigned to only one airplane. Okay, so this tells us this is a one-to-many relationship, and this is the ID of the airplane, and this is the ID of the flight. The pilot, which has the ID Social Security ID, can perform several flights. A flight is performed by at least two pilots. Okay, so we have the airplane entity, the flight entity, and the pilot entity. This is all we need. Okay, this guy, the airplane, is gonna have tail number as an attribute. The flight is going to have flight number as an attribute, and the pilot is going to have social security number as an attribute. Okay, next we do the relations. A flight, okay, an airplane is assigned to several flights, so we're gonna have like that. Okay, an airplane is assigned to several flights, so we're gonna have airplane associated with several flights. Flight is assigned to only one airplane, so we're gonna have a 1 here. Okay, and this is assignment or whatever. Okay, next, a pilot can perform several flights, so we're gonna have a relation here, and a pilot can perform several flights, so we put many here, and a flight is performed by several pilots. In this case, we're gonna add an n. Okay. Now, if you're gonna use the min-max notation, you could say, for example, 2 comma star, okay, in place of the n, and this means at least 2 pilots, but as many as you like, which is pretty funny. Imagine like 1,000 pilots. But I digress. So this concludes the entire question. I believe we're just gonna stick to the 1mn kind of notation rather than the min-max, but in case they were asked about that, then you know what to do, I guess. Okay, you have airplane, tail number assigned to flight, you have one-to-many, wait, what? One-to-many, and you have many-to-many, right? And this guy has the social security number, and because this is a many-to-many relationship, we're gonna need to make it a new table. And knowing that we're gonna make a new table, whoever made this diagram decided to add these two as attributes. Okay, but if we don't know that yet, then you don't need to add this in the actual diagram, at least in my opinion. So let's convert it now to the relational model. I'm gonna see if I can remove this. Okay, so we're gonna have 3 tables. First one is airplane. 2 should be enough. Then you have the flight, in which case, okay, 3. I mean, don't worry too much about the numbers. I'm just doing it in my head really quickly to make this go more smoothly. Finally, for the pilots, we're gonna have like this. Okay. Now, this is going to be the tail ID, this is going to be the flight ID, and this is going to be the social security ID of the pilot, okay? Here we're going to have whatever attributes doesn't really matter, and same deal here, okay? Now, we have a one-to-many relationship with total participation here, okay? Obviously, because you can't have a flight that does not have an associated airplane, right? And it's possible that an airplane hasn't gone through any flights yet, if it's like brand new or something, okay? So we have that like this, and because it's one-to-many with total participation on one side, it's best to use a foreign key approach. So we're gonna add the primary key of this thing as a foreign key in this thing, okay? So we're gonna add tail number right here, okay? And remember, this is just extra attributes that aren't really relevant to the question. Next, we're gonna do this relation. It's a many-to-many relation, therefore we need to make a new table, like I said earlier when explaining what the hell this is. Okay, so we're gonna add a fourth table for the assignment of pilots to flights. You can just say pilot assignment for this. Just write it. How do you do that? Look at this. Okay. Let's say pilot assignment with like a underscore or whatever. Okay. It doesn't really matter. Can I move that? I don't know, man. I've never used this before. Anyways, so we're gonna have this here as the ID of the flight, and this here as the ID of the pilot. Or you can go vice versa, with the first one being the ID of the pilot and the second one being the ID of the flight. It doesn't really matter. Okay. This one is more complicated. In general, it's the same idea. Let me just just solve this quickly. So ERM and EPC web trainer includes many exercises. Type of exercise is either ERM or EPC. Okay, an exercise can only be of one type. Each exercise has a level of difficulty. The same level of difficulty can be assigned to one or more than one exercise. So the level is going to be an entity, and this is also going to be an entity. An exercise consists of several contents. This is an entity. Each content belongs to one exercise only. Finally, each exercise belongs to a category. Okay, so we have four entities. First one is exercise, second one is level, third one is content, and fourth one is category. Now, I have many exercises. Each one has XID. This is the primary key. And you notice the solution has something called an is-a. This is not something we need to cover. So in this case, I would personally represent this as an attribute as shown here, exercise type. Okay. So it have a second attribute, and this is called exercise type. And it can only be either ERM or EPC. Okay. Next, exercise can only be of one type. We already mentioned that. Each exercise has a level of difficulty. Let's say this is the level. Okay. Like this. Same level of difficulty can be assigned to more than one exercise, but each exercise has only one level of difficulty. So each exercise has only one level of difficulty, and each level of difficulty can be associated with multiple exercises. An exercise consists of several contents, and let's say this is the contents. Oh wait, I drew this one first. Let's say this is the contents. We have a relation here, that, this, okay. Finally drew it in one stroke. So an exercise consists of several contents, so we have many here. Each content belongs to one exercise, so one here, okay? And each exercise belongs to a category. So we also have a relation between the exercise and the category, okay? And one category can be assigned to several exercises, so we have many here. And each exercise belongs to a category, to one category exactly, so we have one here, okay? Okay, now I forgot to write the attribute here, the ID. Okay, now let's convert this to the relational model. So let's start first with the level table to make things easy. Level table just has the ID and extra attributes, very easy. Next we have the category. It's on the one side of the one-to-many, so just like the level is gonna look the exact same with the category ID and extra attributes that don't really matter, okay? Such as like the type or whatever, season distribution, master data, whatever, it doesn't really matter. Next, we have the, what's it? Content, okay? The content is on the many side of the one-to-many relation. So in this case, assuming this is like total participation on the one side, I guess. So every exercise needs to have that. Then when we're gonna have a table for the content with the content ID and the associated exercise plus extra attributes, okay? Finally, we have the exercise itself, and this is gonna have actually quite a lot, as you can see here. So we're gonna have the actual ID and then the type. Remember the is a thing from down here. We're representing this once again, like I said, we're representing it as just another attribute, as we can see here. So we're gonna have those two as attributes, the ID, exercise ID, and the table, the type of the exercise, ERM or EPC. Third thing is going to be, because it's involved in a one-to-many relationship and the many is on this side, and we suppose that this is a total participation here. In that case, we're gonna have a, what's it called? Yeah, a foreign key approach, in which we take the primary key of the level and put it as a foreign key in the exercise table, okay? So we're gonna put a level ID here. And similarly, with the content now, category, because we have the relation like this, with the one-to-many and one being on the category side and many being on the exercise side, we need to add the primary key of this as a foreign key in this, okay? So we add the category ID as an attribute here. Finally, we have extra attributes that don't really matter. Check the solution. This is fine, this is fine, this is fine, and yeah, it's okay. And notice here that despite whatever thing was done here with the is a sort of triangle, this still ended up being just a normal attribute, okay? Uh, okay, this one's too complicated. I'm not gonna bother with this one, honestly. It takes too much time, and I want to get this video out sooner than later. Okay, so this one has kind of an interesting thing with the recursive, what's it, relation here, also known as a unary relation. So let's go over it quickly. We have the items entity, category entity, unit of measure entity, and the vendor entity. So we have four entities here: item, category, unit of measure, and vendor. Okay. Next, the item belongs to a category. Item belongs to category. That's fine. There's a hierarchical classification system of item categories where each item category is assigned to exactly one category hierarchy. Okay. Each item category is assigned exactly to one category hierarchy. So this is kind of an inheritance type of thing, I guess, where the entry here is just the ID of a different category, right? Okay. Next we have the items have a unit of measure. An item is uniquely assigned to a UOM. Each item has a single unit of measure, but the same unit of measure can be assigned to multiple items. Okay. Finally, the vendors. A specific item is supplied by more than one vendor, and each vendor supplies several items, so we have a many-to-many relationship. And because it's many-to-many, we need to make a new table, that's for sure. So we add these as attributes if we like. Okay. Next is the conversion to the relational model. So I have item category. First we have the ID, of course, and then the kind of the category that the category belongs to, kind of in the hierarchy. So like you have this category, another different category, and this one this category, and then you have like a higher level category, and all of those are gonna have as a foreign key the primary key of this one. Okay. And then this one, assuming it's like at the top of the hierarchy, it will just have this field as null, let's say. Okay. Sorry for that. Clear this. Next is the item, because this is one-to-many. We're gonna add the foreign key of the item category also as an attribute in the item, and we have that right here. Now keep in mind, most of these exercises are assuming that there is total participation on one side here. Okay, if it was partial participation, which is pretty much implied here by the diagram, even though it's actually total participation, when you have partial participation, you're gonna make a new table, relationship relation, right? But since these are secretly total participation, you're gonna just add it as a foreign key. So keep that in mind. These exercises aren't covering everything. Moving on, unit of measure, it has the ID, and once again, item is on the many side of the relation. So we're gonna add the primary key of this as a foreign key in the item table. Okay, and that's this right here. Supplied by, this is a many-to-many relation, so we're gonna have a new table with the primary keys of both entities as attributes, foreign keys here, and the combination of these is going to be uniquely identifying a pair of item and vendor, okay? And you might have extra attributes like, say, the pricing or the quantity that they have in the inventory, whatever, okay? Finally, the vendor just has this attribute and nothing else. So we add it and make it a primary key. This example is not so interesting. We've already seen similar stuff before, so I'm not going to cover it. So we have this guy, which is unreasonably complicated, and we have this guy, which is already stuff we've seen before that I don't cover. So yeah, I think that's it.